Now this particular question involves a ball bouncing off the ground. It sounds simple enough. However, it's a little bit tricky. The first part of the question asks us to calculate the magnitude of the impulse received by the ball during a collision when it hits the ground. We've been given the mass of the ball as 0.5 kilograms, moving downwards at 4 meters per second just prior to impact, then rebounding upwards with a velocity of 2 meters per second upwards just after the impact. And we've also been told that the ball is in contact with the ground for a period of 0.080 seconds. Impulse is change in momentum, so calculating the magnitude of the impulse simply involves calculating the magnitude of the change in momentum. And even though the question asks for magnitude, it is still important to define a direction as positive. So what we do here is let's let upwards be positive. It doesn't really matter, but we'll make it upwards as positive. There is an advantage to doing that for part B, but not for part A. That means the initial velocity is -4 and the final velocity is +2. So change in momentum, being mass times change in velocity, becomes final velocity of +2 upwards, take away initial velocity of -4 downwards, is a total change in velocity of 6, multiplied by the mass of the ball, 50 grams or 0.05 kilograms, gives us an impulse of 0.3 kilogram meters per second, or Newton seconds. So that's the magnitude. Now the next question is the tricky one. It asks for the magnitude of the average force applied to the ball by the ground during the collision. And we need to be aware that when the ball is in contact with the ground, it's not just subject to the normal reaction force upward, which was the actual name for the force applied to the ball by the ground. This statement here is equivalent to normal reaction. And we're asked to calculate normal reaction, not the net force. However, we begin by using the impulse equation to calculate the net force. Impulse equals force by time tells us the net force acting on the ball during the collision must have been 3.75 newtons upwards. And as I've noted, this is the net force applied to the ball, which is a combination of two forces. The ground pushing up, normal reaction, and of course the weight of the ball, mg. And if we apply those two to the net force equals n minus mg, taking upwards as positive still, we have n equals 4.25 newtons, bigger than the net force.